Question B1. This question is about quantum physics and electrons. A. Photons of frequency 2.1 times 10 to the 15 Hertz strike the surface of uranium and electrons are emitted from the surface. The work function of uranium is 3.6 eV. Show that the maximum kinetic energy of the emitted electrons is about 5 eV. So we're working with this whole photoelectric effect, and these two formulas relate to the photoelectric effect. Obviously this formula is incorporated into that. That's the energy of a photon. So we have our incoming energy from the photon. This is our work function, and this is the maximum energy, maximum kinetic energy of those electrons. So we can work with that. I'll just bring out the calculator here. We're going to have the HF is equal to, here we've got 2.1 times 10 to the 15 times 6.63 times 10 to the negative 34. That's going to give us our HF, so let's just calculate that. So we're going to get 2.1, remember I always use that for my scientific notation, 15 times 6.63, and then use that minus sign over there, 34, and I get 1.39 times 10 to the negative 18. We never use this notation, this E notation. We always, that means times 10 to the. Now that's in joules. Now we need to put that into EV. So that's to go from joules to EV. We obviously have to divide. We divide by 1.6 times 10 to the negative 19. So let's just do that. So I'm going to divide my answer by 1.6 exponent negative 19, enter, and I get 8.7 times, EV, no times 10 to anything. So that's the energy that's coming in. Now the work function is 3.6. So from this formula over here, let me just go back to here. From this formula we have this over here, this HF is equal to our 8.7. Our work function is 3.6 plus our E max. So it's just going to be 8.7 minus 3.6. We're looking at about 5.1 EV, which is approximately equal to 5.0 EV. So we've proved it there. So explain what change to this energy would occur if light intensity was doubled. Now the intensity increases the number of photons, but not the energy of those photons, so there would be no change. No change. This light intensity, that increases, that sends up the number of photons, but doesn't increase, no change in HF, because the frequency is staying the same. Looking at question B, the de Broglie wavelength of an electron with energy 5 keV is lambda. Determine the lambda. So we are obviously going to be using this formula over here, because this is our formula discussing or talking about the wavelength related to a particle. So we have lambda is equal to h over p. Just change that around. This p, you know, is the momentum, and that h is Planck's constant. Now we are told that it's got an energy an electron has got an energy of 5 keV. Now, we can actually work out the momentum because basically I know this, but I need to find out what the momentum is, and from that we'll be able to work out what our lambda is. And so I need to find out what my momentum is, and I can do that because I know what the kinetic energy is. And I'll just go through this process again. We have that Ek is equal to a half mv squared. So that's, I can write that as m squared v squared over 2m is equal to my Ek, my energy. And we know that because P is equal to mass times velocity, I can write this as P squared. So we've got Ek is equal to P squared 2m. And therefore P, if I change this around and multiply both sides by 2m times by 2m cancels, I've got P squared is equal to 2m Ek. And if I take a square root, it's equal to 2m Ek. So I can therefore replace this h, not replace h, replace the p by the square root of 2m Ek. And I can put in those values. So we're going to get 6.63 times 10 to the negative 34 divided by the square root of 2. Now this is the mass of an electron, and the mass of an electron is 9.1 times 10 to the negative 31. 9.1 times 10 to the negative 31. That's given in your data booklet, times your Ek. And your Ek is 5 eV, but we'd need that in joules. So that's going to be 5, sorry, not 5, is 5 keV, sorry. It's this one over here that we're talking about, 5 keV. So that's going to be 5,000 eV. And we want to put that in joules, so we have to multiply that by 1.6 times 10 to the negative 19. So I'm going to need to put that in. So it's going to be times 5,000, or 5 times 10 to the 3, times 1.6 times 10 to the negative 19. And I need to put that all into my calculator. So let's bring up the calculator here. Bring that up here. I can clear that. Let me clear this ink also. So we've got 6.63 exponent negative 34 divided by, and here we are getting the square root, so it's a square root, and we want to put this all into brackets in the square root, so it's 2 times 9.1 exponent negative 31 times, I'm just going to write this as 5,000 times 1.6 and I've got the exponent negative 19, and then I'm going to close my brackets at the end, push enter, and hopefully I get something reasonable, which does seem to be. So I get my lambda, my wavelength, is equal to, now I've got obviously a number of significant figures here. Here we are working with two significant figures, so I'm going to work with two significant figures, 1.7 times 10 to the negative 11. Remember, we never use this E here when you're doing it, and that will be meters. Good, so then it says over here, student makes a statement, the electron wave is not real, it is just a mathematical construction, electrons are particles and never waves. Outline evidence which suggests that the student statement is not correct. Well, it's not correct because when electrons are pass through a very narrow slit, a crystal, they diffract. You get diffraction patterns. So because you get diffraction patterns, this shows that electrons are waves. Because when you pass them through a crystal. And C, outline how 1. The electron box model accounts for the existence of discrete energy levels in the hydrogen atom. So the electron box method basically says is that we can view electrons as standing waves in a box, a one-dimensional box, 1D box. And because of that, you can only get certain wavelengths. Now, from our formula, that P is equal to H over lambda means that you only have certain momentums, only certain P's, and therefore only certain energies. Because remember, we can write that your EK, your energy, is equal to P squared over 2M. So if these are only certain amounts, then you get only those. Now this formula over here, if I just close this, clear ink, go here, just clear that also. This formula over here shows that, in that your kinetic energy, this comes from your electron box model, but your N here, this N, are your natural numbers, 1, 2, 3, 4, and so forth. And because they're your natural numbers, you're going to get only specific energies that are coming out. And then the final question here, it says, line spectra of atomic hydrogen provide evidence for electron energy levels in the atom. Well, we know that each line is a well-defined single frequency. So each line corresponds with a certain frequency. And because you have your E is equal to HF, you have certain energies. And as they go from one energy level, as you go from one energy level of a certain energy to another one over there, it will give out very specific photons of certain or specific energies.